Alright, in this video we're going to introduce the vastly superior unit for measuring angles known as radians. So we'll talk about what a radian is, I'll show you how to convert between radians and degrees and vice versa, we'll talk about technology, and then we're also going to just go over all the material from earlier in the chapter one more time, this time thinking in terms of radians. And I'll also include some alternative ways to think about things that I cut from the other videos due to time. So hopefully by the end of this, not only will you have a basic understanding of what radians are and how they work, but hopefully you'll also have a better understanding of the material that we've learned so far. So we've got degrees already. We know them, we're comfortable with them, so why do we need another unit? So now what is a radian? Well, first, to compare it to a degree, the way that I think about degree measurement is if I were to take this red line segment and try to move it, rotate it, to cover up this purplish line segment. Again, I am colorblind, so I'm sorry if those were off. The degree measure is really thinking about the rotation. It's thinking about what angle do I have to rotate this red line segment to cover the purple line segment? And that should seem obvious. I mean, of course, an angle is about rotation, right? But when we think about radians, what we're considering more is actually the distance that the tip of that red line segment would travel around the circumference of the circle to get to the tip of the purple one. And when you think about it, that's really an equivalent way to think about rotation. And instead of thinking about a turning of the object with a pivot point here at the center, you can consider how far would the tip of it travel. And that's really what radians are, or at least how I like to think about them. So a radian, which we see down here, is just an abbreviation of radial angle. A single radian is going to be the angle that we would have to rotate through so that that distance is equal to the radius of the circle. So obviously, in the image that I drew, it seems like that arc might be a little bit less than the radius of the circle. So I would say that this degree measurement would be a little bit less than 1 radian if I were to draw in this one instead. Now certainly, the distance covered here is definitely less than that radius. So this angle here would be less than 1 radian for sure. If I were to draw this angle going all the way here, now this distance is clearly larger than the radius, so this angle would be more than 1 radian. Now when we write down an angle that's measured in degrees, we know that we use the degree symbol, that little circle in the spot where an exponent might be next to the number. When we write down an angle in radians, if we were going to put any symbol, we would use basically the letter C, and that's because that letter C is supposed to look like the arc of a circle, so just like the arc we were traveling along up here. However, in practice, we generally don't actually write down that unit. So if I ask you what an angle is, and you tell me the angle is 27, I now assume that you mean 27 radians. The only way that I will assume that you mean degrees is if you put the degree symbol. So now how can we convert between these two? Well, let's think about our unit circle again for just a second. So now we have a radius here of 1. Since we're talking about going around the arc of a circle, let's consider going all the way around this circle. What is the diameter of this circle? Well, diameter is going to be 2 times pi times the radius. We said the radius is 1. So that means that the circumference is 2 pi. But the circumference is the distance going around the circle, which means that 2 pi is also the radian measure of an angle that goes all the way around. In other words, 2 pi radians represents the same angle as 360 degrees. And from this, we get our conversion. 2 pi equals 360, that means that pi is equal to 180, and that's what I recommend that you remember. To go from degrees into radians, you just take your degree measurement and multiply it by pi divided by 180. Radians back to degrees, multiply by 180 over pi. When it's possible, we want to give our answers in radians in terms of pi. We want to be exact. We do not want to use a calculator to get a decimal approximation. So when we're dealing with 45 degrees and we want to write it in radians, we're going to take 45, we're going to multiply it by pi over 180, and we're just going to think about, hey, what's 45 over 180? 45 over 180 is the same as 1 over 4, so that means our answer should be pi over 4 radians. You could also think about it in a different way here. We know that 180 is the same as pi. 45 is the angle we care about. That happens to be 180 over 4, so 180 over 4 should be pi over 4. Same thing. Now in this case, the exact angle was easy because 45 goes into 180 very nicely. It's not always going to be the case. So if I did have a degree measurement like this, 126.5 over 180, that's not a convenient fraction. It doesn't simplify nicely. So for something like this, I might give a decimal approximation. No one's going to say that 45 degrees is about 0.785 radians. They're going to say it's exactly pi over 4. And if we wanted to go back the other way, again, if we have a radian measure that includes pi, that means we should be able to get a nice degree measurement out. Because when we multiply by 180 over pi, right, so we can cancel those two, and even the 180 over 6 is just going to be 30. So we got 5 times 30, and that's 150 degrees. Awesome. In the second case, that's already a decimal, probably approximation. So we're just going to multiply by 180 and divide by pi. We're going to grab our calculator, press the pi button, and we'll get an approximation out for our decimals. Yes, it's true. 0.638 radians is equal to 114.84 divided by pi degrees. However, that's really not said. We generally do not include pi within an answer that's given in degrees, although technically 114.84 divided by pi is an exact answer in this case, whereas 36.6 is a decimal approximation. So there is something nice about having an exact answer. Of course, I'm generally in favor of that, but just conventionally speaking, we tend not to include pi in our degree measurements. And look, if you're ever in any doubt, if it's on a quiz or a test or something, just read the instructions. It'll probably tell you what form to give your answer, and if it doesn't, then just give a right answer and don't stress out about it. Now, it's great that we've got the conversion down, but we don't want to have to use that formula every single time, especially when we're dealing with very, very common angles like those that we've seen previously, the multiples of 30 and 45 degrees. So we should be able to convert those into radians either by memory or at least very, very fast, hopefully without having to think too hard about what the formula is. Like, I think you should know that 30 degrees is pi over 6. And at first, it's okay if you don't remember that, that's fine. You can always get to it by thinking, well, pi is the same as 180, the 30 is a sixth of 180, so then that must be pi divided by 6. You can work these out using the formula, of course, but it would be really nice if you could get to the point where you see pi over 6 and you know, yes, that is 30 degrees, without having to think about 180 being pi. And likewise, 45 degrees is pi over 4. 60 degrees is pi over 3. This one could be a little confusing for some people because you've got this 3 and 6 and this 6 and 3. I don't know. Just memorize that they swap or something like that. And then from there, the rest of these, you could work out that 150 degrees is 5 pi over 6, again, by using the formula. Or if you know that 30 degrees is 1 pi over 6, then you just need to think, well, 150 is 30 times 5. So that means I'll take pi over 6 times 5 and get 5 pi over 6. And in that way, you can generate a whole lot of these angles in radians. If 30 degrees is 1 pi over 6, then 60 degrees is 2 pi over 6, and 90 degrees is 3 pi over 6, and 4 pi over 6, 5 pi over 6, 6 pi over 6, all the way around to 12 pi over 6 to get to 2 pi, 360 degrees. And if I wanted to know 390 degrees, well, that's just 30 degrees more. So that's going to be 12 pi over 6 plus 1 more pi over 6. That's going to be 13 pi over 6, and so on. Now, when we are using our calculator to perform a conversion from one to the other, we need to be careful. If you include the pi in your fraction, it's going to get you the decimal approximation. So what I would recommend is just leave the pi out. If your calculator is set to give you exact answers, then it'll give you the fraction out, and then you know, okay, it's 7 over 6 times pi. If you have your calculator set to automatically give you decimals from fractions, then I recommend changing that setting. You can do that by going to doc 7.2 and making sure that your calculation mode is set to auto rather than approximate. It also does not matter if you're just doing conversions. It doesn't matter what setting you're in up here, whether it's degree or radians. That's only going to have an effect when you're doing something that explicitly has a trigonometric function on screen. So when I ask the calculator, what's the sine of 30, and I'm in degree mode, I get 1/2. If I'm in radian mode, I get garbage. But if I ask it, what's the sine of pi over 6, it'll tell me it's 1/2, unless I'm in degree mode, in which case it'll give me garbage. I mean, this is technically a correct answer. It's just telling me the sine of pi over 6 degrees happens to be this very, very small decimal. When we go to graph, we need to think about units as well. Right now my calculator is set to degrees, and I've graphed the cosine of x, but this looks like a horizontal line at 1. So what's going on here? Well, it makes sense that it's going through 0, 1, since that's what the cosine curve should do. But I can't see the rest of it because in degrees, my x values have to go all the way up to 360 if I want to see a complete repetition. So I could change my window and change my x max here to a larger number. And now I see a cosine curve. But if I were to try graphing the same thing in radian mode, now all of a sudden it looks crazy. But that's because seeing out to 400 radians would be a whole lot of times going around the unit circle. So now I would want to change my window zoom to give me something more like, well, a little bit bigger than 2 pi. So let's just go with something like 8. And there we go. Now I see my cosine curve in radians. If you're working within Desmos, you also need to be mindful of this. Right now this graph looks like it's set in radians, and that is the default in Desmos. If you go over here, click the wrench, you'll see that we are in radian mode. If I change it to degrees, I have the same issue that I had on the calculator earlier. I could change my x max here to a large number. Now I see my cosine curve as I would have expected. If I go back to radians, it's going nuts. So I want to change these to be smaller numbers. The nice thing in Desmos actually is that you can just type in the letters pi and it'll automatically type the pi symbol for you, which is pretty cool. 2pi, there we go, 2 pi. And there we have it. Oh, the other thing you can do in Desmos is you can change your step, which is going to change the numbers that we see here along the x-axis. So, I mean, I can interpret this as looking at one complete repetition. It looks like right over here somewhere. Oh, the graph will even tell me that's exactly 2 pi 1. So 2 pi is going to be right around here on the x-axis, but it'd be nice if we could see that exactly. So we can just change the step to give us something in terms of pi. I mean, you could just type in 1 pi. That's great. We already see a few angles populating there. Let's say we made it something like pi over 6. So that'll give us all the angles that are multiple of 30 degrees showing up. So that's very nice. And pictures like this for either sine or cosine, this will help you, again, practice your conversions between angles measured in degrees and radians. You know, if you're thinking in terms of degrees and you know, okay, well, the sine curve has a maximum at 90 degrees, well, I can just check right here. Okay, 90 degrees is pi over 2. And you can just, you know, start to think about these graphs with your x-axis in radians rather than degrees, and you'll start to get used to it. Speaking of graphs, I left this out of the previous video because I couldn't find a good animation online that was done in degrees, but I did find quite a few that were done in radians. So this is just another visual to help us see where these graph shapes come from. So what we've got going on here is there's a unit circle, and we have a point rotating around that unit circle. And I'm going to generate a graph here for, let's do the cosine graph first. Remember that cosine is going to give us the x-coordinate of that point as it moves around the unit circle. So I want you to think about what the x-coordinates are as it moves. So right now the x-coordinate's 1, and it's decreasing to 0, and then it's decreasing further to -1, and then it's moving forward to 0, and moving forward to +1. And then that pattern is going to repeat. Back to 0, back to -1, to 0 again, and then to +1. When I graph the cosine curve, the y values of this graph are going to match the x values of that point as it rotates around. So right now, the x has it's an x-coordinate of 1, and we have a y value of 1. As we rotate around, we now have an x value of 0 on the unit circle, corresponding to a y value of 0 in my cosine curve. And we continue. Let's let that go. The y value of the cosine curve matches the x-coordinate of the point as it rotates around the unit circle. I think this visual is very nice for giving an understanding of where that picture comes from. I know we looked at tables last time, but I really like seeing it in motion. And we can do the exact same thing with sine, but in order to do that, we need to remember that the sine function gives us the y-coordinate of that point. So let's start it back here at the beginning, and let's see how it goes. The y-coordinate started at 0, went up to 1, back down to 0, back down to -1, and up to 0 again. And then it's going to repeat. And again, our x-axis here is measured in radians. Speaking of things that I didn't mention in the previous video, there are two famous triangles that some of you will have heard of. The 30-60-90 right triangle and the 45-45-90 right triangle, which I think it's worth mentioning these now because they show up very commonly in geometry problems, and they also have the special angles that we're really interested with in trigonometry, the 30, the 45, and the 60. So I want to just give some different geometrical arguments for how we could derive the sine and cosine values of these three angles. So in the 30-60-90 right triangle, which I have here, I'm imagining actually that this is half of an equilateral triangle. And I've decided that the hypotenuse should be equal to exactly 1. And that's because I'm thinking about this point here being a point on the unit circle with a center right there, but we don't need to even consider that to get our answer out. Now, if this side length here is 1, how much does that make this portion right here? Well, we've got an altitude here in an equilateral triangle, so that is going to be perpendicularly bisect this side, meaning that this portion here will have a length of 1/2. Now, using what we know about right triangle trigonometry, what is the sine of 30 degrees? Well, it's equal to opposite, which is 1/2, over hypotenuse, which is 1, and that's just 1/2. And then we could use the Pythagorean theorem to work out what this other side length is, and we would find that it is equal to the square root of 3 over 2. And then from there, we could get the cosine of 30 degrees. Likewise, the cosine of 60 degrees will be 1/2, and the sine of 60 degrees will be root 3 over 2. Over here on the right, we've got a 45-45-90 right triangle. It's isosceles. Since we have two congruent angles, we'll have two congruent sides. Again, the hypotenuse is 1. And again, I would just use the Pythagorean theorem. Since I don't know what these two are, we could figure them out. X squared plus x squared equals 1. Solving for x, we'll find that it has to be equal to the square root of 2 divided by 2. Or if you prefer, 1 over the square root of 2, same thing. And so again, what is the sine of 45 degrees? It's this, because it's just that divided by 1. What's the cosine of it? Well, it's going to be the same thing. More generally, however, what I recommend committing to memory would be the side lengths in the 30-60-90 of x being across from the 30-degree angle, 2 times x being the length of the hypotenuse, and then x times the square root of 3 being the length of the other side. And then for the 45-45-90, I recommend x, x, and x times the square root of 2. These will be true for every 30-60-90 and every 45-45-90. As long as you know what one side length is, you can quickly work out the other two sides. And again, you have options. You could be using Pythagorean theorem, you could be using right triangle trigonometry, you could be using unit circle facts, whatever. There's a lot of ways to come at this, but I just wanted to mention these two special triangles since, as I said, they are very, very popular. And they tend to go by the 30, 60, 90, and 45, 45, 90 names. There's just something about calling it the pi over 6, pi over 3, pi over 2 triangle just doesn't sound as catchy. I don't know. Okay, I've definitely said everything that I need to in this video. The remainder of the time is just going to be me going on about a rant because here's the fact of the matter, folks. I don't like pi. Don't get me wrong now, radian measure is very important. We'll start to see that in the next video. Once you eventually go on to study calculus, you'll see even more why radian measure is the best. But that being said, pi is just, it's a weird unit to use here. I mean, think about it for a second. Pi is the special number we're going to use. But going pi around the circle is only halfway. It's a half turn. And I think it would have been more clever if we chose a unit that represented a whole turn around the circle. So I would prefer a new unit that means 2 pi. And there's a unit that's out there. It's not very popular, but I encourage you to consider its benefits. The unit is another Greek letter, and it's called tau. Okay, so here's a few sample angles measured in degrees and pi radians and also in terms of tau radians. And just think about how much more sense tau makes than pi. If I want to go all the way around the circle, as I just said, all the way around one circle, that's 1 tau. If I only wanted to go halfway around the circle, that's half tau. Makes a lot more sense than 1 pi. If I want to go a quarter of the way around the circle, that's a quarter tau. I mean, they even chose the symbol tau to start with a T, so it sounds like turns. This is literally a quarter turn around the circle. Tau just makes so much more sense. And I didn't come up with this myself. If you want to dive really deep into a mathematical rabbit hole, there will be a link in the video description to the Tau Manifesto. It's tauday.com. There is quite a bit of reading material here, as you can see. There's It's a lot. It's absolutely a lot. And some of the mathematics here, I won't lie to you, some of it's definitely beyond where you're at right now. However, by the time you're finished with high school, most of the math in here should make some degree of sense to you. So there really are, I think, strong arguments to support using tau versus pi. Ooh, I reached the end. Great. And as you can see, there is no shortage of YouTube videos out there going on about tau. There's a lot of people who support tau being a better circle constant than pi. The thing is, you know, pi has a lot of history behind it. We've been using pi for centuries. So people are resistant to change. And so you're not going to see tau referenced in any, well, you're not going to see it referenced in most popular mathematics textbooks. You're not going to see it on an AP or an IB exam, but I encourage you to use it. Use it in my class. I will mark you correct. I think you should use it in all future math classes. And if your teacher's never heard of it, I think you should take that opportunity to teach your teacher something and try to convince them that tau is absolutely superior to pi. But I'm gonna stop myself there. I'll put links in the video description to a bunch of tau stuff because I'm trying to raise an army here, folks. I need you to be on my side. Anyway, that's the end of this video. Again, main ideas here, converting between degrees and radians, whether you're going to measure them in pi or tau, although you should use tau, and start getting into the habit of thinking in terms of radians as you do all of your trigonometry. We'll have a mix in this course. Some problems will be in degrees, some problems will be in radians. You're going to need to be aware of what unit the problem is in, aware of what unit your technology is in, aware of what unit your answer is in, making sure to include the degree symbol if your answer is meant to be in degrees. And I know that they might seem strange at first, but you got to trust me on this. Degrees are not helpful when you're doing more advanced mathematics. We absolutely need to embrace radians. So hop on board, but hop on board Team Tau.